So, welcome to the Devirtualization talk. My name is Piotr Padlewski. I'm an undergrad student at the University of Warsaw. I also work in IIT, where right now I develop with my team some static analysis tools. And it's very nice to be here, especially thanks to the LLVM Foundation, because I got the student grant, so I couldn't be here without it. So I'm going to talk about the virtualization LLVM. So let's start with what can we do in the front end, right? What optimization do we do right now? So in this simple case, we have a struct, and we call the same function 2 times. So this is an obvious thing to do in the front end because we have we can look at the AST. We have a type of this class, so we can just change those 2 direct calls. Just change those 2 virtual calls to have direct calls. So this works. So what else can we do in the front end? So if we don't have a type that the final type that we are calling this function, then when can we change this indirect call to be a direct call? So if you have a final keyword, this is C++11 final keyword. This tells optimizer that this class can be overridden. So this function is also final, so we can change it to be a direct call. And optimizer can do it. The same thing with a final keyword. On the function, client also do this optimization. And surprisingly, there is one more thing. When you have when the class is in anonymous namespace, and we know that this class is not overridden by any other class, then we also could change it to be a direct call in a front end. We don't do it right now, but fortunately, because it's a static class, so we will have all the definitions of all the virtual functions. Then, and because it's static, inliner will be much more happy to inline calls, and then it will probably devirtualize most of the stuff. Okay, so what about the middle end? Here we call function g. So obviously, frontend cannot do this optimization because it requires inlining. And middle end will handle this case. And this is because it would just do a simple store to load propagation. We have a constructor stores v-pointer, and then we call function that loads the v-pointer. So this call will be changed to be a direct call. But fortunately, if you don't have a constructor, then everything breaks. Okay, and LLVM right now won't be able to devirtualize this case. So let's look at LLVM IR. So this is before inlining. As you can see here, we have 2 loads. First is loading a vtable pointer, is loading vtable, and second one is loading the function, right? And then we call the function. So if we can't inline the constructor, then it won't gonna work. But if we have constructor, then it will look like this. We have a store of v-pointer, and then GVN will figure out what we are doing here, and we're gonna call this function. What else? If you have 2 calls, virtual calls, then we know that the first one will be devirtualized, as you saw in the first example. But unfortunately, the second one won't be devirtualized. So let's look at LLVM IR. So as you can see here, the first one got devirtualized, but the second one, like, we had just normal loads and then call. So this is because LLVM assumes that the v-pointer is changed. It might be changed because we are just calling some function that we don't know the definition, right? So it assumes the worst. And there is one more example, and this is really tricky. So I just added the virtual destructor that is default. And Surprisingly, this also will fail. So let's look at LLVM IR. So you can see here we have a store of the pointer, and then we'll have load, right? So like, what happened here? Why did it not work, right? Right, we have those two examples. The first one got devirtualized, the second one doesn't. So the answer is there are some problems with Itanium ABI and how Clang is emitting some functions. So surprisingly, the vtable will be external in both cases. Okay, so the question arises, okay, so where is my vtable, right? And there is something called key function optimization. The goal of this function is just reduce is to reduce the code size. We want to put the vtable only in one place. And the rule is that we put vtable in a place where key function is defined. And the key function is the first non-pure virtual function that is not inline at the point of the class definition. Okay? But see that actually this structure doesn't do anything with this key function, right? It's because our key function is foo, right? So why did it did not work? And why did it even work in the first example if they are both external? So we have something, we have, in LLVM we have this linkage called available externally, which says that this thing will be external, but we'll just give the definition just to do some optimization, and then we have to just discard it. So it worked in the first example because we could emit available externally vtable. And it was not safe in the second example because Itanium ABI doesn't guarantee that any virtual function will be exported. Okay, and Clang is really lazy about emitting virtual inline functions. Okay, and this is actually good because as I talked with John this morning, GCC is actually producing like 20x stuff during the compilation. It's like these old inline functions that it doesn't really need at the end. Okay, and Clang is trying to only emit inline functions that it uses, and it have direct calls. So what about this ABI thing? So let's just picture it. So we have this one module that has this function f, and we'll have the implicit call of the destructor, and we have another module that defines the vtable. So firstly, the vtable is there, so we know that the function foo will be there. Okay, and we also know that this function has to be there, right? The destructor. But the problem is that it might be hidden. We are sure that it's there, but it might not be exported. So it is not a very good idea to assume that this function will be defined somewhere and try to call it by having a direct call to it. So what we have to do is we have to define the function in the same module, and then we can make direct call. So, and I know that this is not a really good example because we actually have to emit this virtual inline destructor here because we do direct call here. But the problem here is that, so right now, available externally vtable is emitted only if it's not emitted if vtable contains one of the inline methods or hidden visibility methods. And like one solution is like we could just emit all the inline virtual functions, right? Then it will be safe to emit available externally vtable, but it will be very, very slow. The other solution that is much, much better is that we could emit the available external vtable if we would be sure that we actually emitted all the inline functions in this module, right? So Clang doesn't do it right now, but it could. It could be done there. So the Holy Grail of Devirtualization. So if you want to change, if you want to have a direct call from the from indirect call, we need those three things, right? We need a v-pointer value. We need to know what v-pointer is pointing to, what v-table it points to. We have to know that v-table definition, and we also have to know that the v-pointer is not clobbered after the virtual call. So what about the last thing? So what is the semantics of the virtual functions? So can v-pointer really change? Like, obviously it can because it changes multiple times during the construction and destruction of the object. It has to be set multiple times because we can call virtual function inside the constructor, and this virtual function have to call the right function. It cannot. It won't call the derived virtual function. It has to call the base virtual function. But can it really change after calling a virtual function? Right. This is the key question. So, what if I have something like this? I have a virtual function, and I assume that derived is derived from base. They have the same size, and I am just using placement new inside of this object, right? I know this is evil, but like, who thinks that standards allows this? Okay, there's one people who think that it doesn't. Okay, most of the people doesn't have an opinion on this. So, unfortunately, standard allows this. You can do this evil code, right? You can change v-pointer while calling a virtual function. But fortunately, calling the same function, like with the old pointer, is undefined behavior. So what standard says is that if I have a pointer to object and the lifetime of object just ended, and calling displacement new ends the lifetime of this object because I just put some other object inside of this object. Then this pointer is dead. Okay, this is a zombie pointer. I cannot use it. And calling any function on this, dereferencing, all the stuff, this is undefined behavior. But if I will have this, if I would just return this pointer and use this pointer, then this is completely fine. Okay, so we have to be aware of the cases like this. But it is safe to assume that two virtual functions using the same pointer will call the same function. Okay, and we have to be aware of all these corner cases. Okay, so how to teach LLVM not to clobber v-pointer? So we want to say that the v-pointer is invariant, right? So we have this intrinsic called LLVM invariant start and end. And what this do is like just that memory starting from this point to this point is invariant, okay? But the problem with that is that we have to see the construction of the object and the destruction of the object, which is not, it could be across different functions. So it's not really trivial to use it. So it doesn't really fit. There is also invariant load that we could put on a load. And what they do is they're saying that this memory location is invariant for whole program. Okay? So it also doesn't fit because the pointer changes like multiple times. So we decided to add something new, to add something called invariant.group metadata. And let's look at the semantics. So firstly, we can put it on a loads and store. Okay. Then if optimizers see two loads, or like loads and store, with the same pointer operand, so the same argument, and the same invariant group metadata, then it can assume that those two loads are loading the same value. So it can just remove the second one and use the value that the first one is producing. And Bitcast doesn't affect it. So, okay, so how to handle all the cases? Because of course, LLVM is smart enough to figure out that two pointers are aliasing, right? If I just calling a placement new, placement new is just calling constructor with the pointer. So this obviously would break. So we decided to add something that could help us launder the memory, which is LLVM invariant group barrier. And this intrinsic is only taking a pointer and return the same pointer. It's like, but of course, because it's intrinsic and optimizer doesn't see the definition of this function, then it won't know about it. So if we do start and see like what's the value of this pointer, then it will just go to the barrier and stop because it doesn't know anything about it. And we have to add it in every place where dynamic type changes. So what's the status of this feature? So optimization right now works for a single basic block. I want to write a patch soon. It's basically in a memory dependency analysis. It just requires a lot of refactoring. And Clang decorates vtable loads when you pass a strict vtable pointer flag. And of course, we have to add those barriers in all those corner cases. But there are some problems with this approach, unfortunately. So firstly, of course, adding the barriers will have some misoptimizations, right? We didn't have a barrier. So for example, we were storing 42 to some integer in a constructor. Then we add the barrier. We don't know what's the value of this integer, right? And there are a couple ideas how to handle this. So one idea is we have to teach important passes that would have these misoptimizations, how to go through the barrier without breaking the semantics of this whole invariant group. So, like for example, if I have this load, and like I'm not really sure if it's correct, but I think that if I would have a load of the like storing the 42, and it won't have any invariant thing, and I will have load of the same location, and it also won't have any invariant group attached, then possibly we can go through the barrier and see what's going on. The other solution, we could strip all the invariant group metadata and all the barriers when all the devirtualization is done, and then we could do the other optimization. But there is a big problem with that, is that most of the devirtualization is done in a GVN, and we run GVN only one time. And also the other optimization that occurs, most of it, I think most of the misoptimization would come up from the GVN. So it's not really that easy. And there is also one corner case that is not handled right now. So as you can see here, I'm creating object, calling function, and then doing a placement new on this object and taking new pointer. And then everything is OK, except that I just got assert. And assert is killing it because assert will generate unreachable at the end of the branch. And so optimizer will know that, oh, A and B is the same. So I can replace A with B in all the places. And if we will just put A there, then of course it won't gonna work. It could call wrong function by devirtualization. Some solutions, we could add barriers before in the comparison. Like I don't think that there is much code that checks for 2 pointers, so it probably wouldn't be a big problem. We could add barriers on the other places. I'm not sure if it solves all the problems. I hope so. Okay, so let's talk about the constructor, right? As you saw in the example when we had an outline constructor, then optimizer wouldn't know what's the value of the v-pointer. So we decided to add three functions. Like firstly, let's load the vtable, then compare it with the vtable that it should point to. Like let's load the v-pointer, and then call LLVM assume. And this intrinsic is telling optimizer that this flag, this compare vtable value it can assume that it's true. So then, if we have use of the vtable, we can just replace it with the constant that we got there. What's the status of this? So firstly, there are some big problems because we firstly wanted to make it as default. And there are some big compile time regressions, mostly in the inst combined and caused by assume cache. So what assume cache is trying to do is that it sees multiple assumes and it's trying to figure out value of some pointers and other stuff. And it's trying to combine many assumes with each other. And of course, it doesn't give it any new information. And if we happen to have like 10 to the 6 of like global objects or something, dynamic object, and we have this big initializer, and it will generate all these assumes, then it's gonna be slow. So I'm not really sure how to solve it. I mean, I'm pretty sure that there is some solution, but I'm not really familiar with the assume cache. So assume loads were temporarily disabled by default, so they require also strict vtable pointers. There was also some problems that if we generated those assume loads, it could be the first reference of the vtable in this module. And it caused some problems. So right now it follows the same rules as available externally, of generating available externally vtable. Okay, so I will show you a demo, not live, but on the slides, just so you know, like how the devirtualization with strict vtable pointers works. So we have an example like this. We have outline constructor, so one thing that didn't work for us first time, and we have multiple calls, right? So we'll inline the function, and then we'll see what happens. So firstly, let's look at the call foo. So this is all optimization without the strict vtable pointers, right? For each call, I will have just those two loads and call. So if I will put invariant group here, then this is what will happen. I would just eliminate those two extra loads of the vtable. As you can see, I'm still loading the value of the vpointer. This is actually something that we didn't think about it when we were designing it, because it actually doesn't matter if we want to have a direct calls. Because if we would know that this loads some, if we would have a vpointer value, then we would know that it points to a vtable that is constant. So those three loads will load the same value. But what we can do is we could attach invariant load, which is saying the same thing, that those three functions are the same, like the memory location is the same. And then what will happen is this. So we'll happen to have the same function called 3 times. Okay, so what happens after inlining? This is before inlining. So as you can see, we will have this assume loads, and then after inlining, it will look like this. So right now, inst combine or some other pass will simplify it, and it will just use the first load, right? And then the information from assume will just come, and GVN will do this. So you'll have 3 direct calls. Okay. So let's talk about some other optimization that could be done to do more devirtualization. So first thing is speculative devirtualization. So basically speculate that one function will be called much more often than some other function. And we just speculate by adding a branch. We are just adding a branch, and we will have direct call. And because we will have this direct call, we can inline this call, right? And what we can do here is that we can either compare a value of vpointer or the value of the function. I think that GCC is comparing the value of the function. There are just two different approaches. For example, if I compare value of the v-pointer, then if I have many, like multiple calls on the same object, virtual calls, then I can just put it in a one branch. But if I compare the value of the function, then one function could be not overridden by many classes. So one branch could just works for many classes, right? And I think the best place to put this would be in the front end. And this is because it would also works very well with the problem that we got with the available externally vtables. So like if client won't see a direct call to some function, it won't gonna just emit the function. But if we will start to put direct calls like this from the speculative devirtualization, then it might like to generate available externally vtable then. And there is interesting problems that arise here. So suppose that we do all the speculative devirtualization, and then we didn't inline the function because it was not tasty enough, right? It was too big or something. So what we have to do is that we should probably do the reverse devirtualization or virtualization. And we should just remove the branch and just fall back to the normal virtual call. Okay, but speculative devirtualization could be very inaccurate. If we have a profile information, then what we can do is we can do indirect call promotion. And so basically, we can do it much more accurately, right? Because we know what functions are called much often inside one of the function. So, and it also works on any indirect call. So it could work for C, C++, and it actually is implemented right now in LLVM. And it is implemented on LLVM level, and this is really important to understand it because we cannot just do it in a Clang because we want to do other specialization of this of the call that will be called in different functions, right? So if we will happen to inline the same function in many places, and we call in the multiple places we call it with different objects, then we'll have a different outcome. And it has to work very well with this speculative devirtualization, because if we will just start putting this speculative devirtualization, and then we'll have a profile data, and LLVM will see that this call is dead. It's never called. Then what we should do is we should really do the same thing with this reverse devirtualization. We should just virtualize it, remove the branch, and fall back to normal virtual call. Okay, but we can do much more fancy stuff if we have a whole program, information about whole program. So, firstly, if you know the full inheritance graph of the classes, then we know that some classes or some functions are not overridden, right? But one problem here is that we can't really know the full inheritance graph, because we could have dynamic libraries if we call that could overwrite our classes. And so right now, what LLVM is doing is that, or Clang, it assumes that some classes in some namespaces are open and some are closed. And by default, everything in std namespace and stdx or something is assumed that it is open. So like other libraries that we use could override those objects. But everything else is considered as closed. We can change it by using some flag. And of course, we can do other analysis and speculation. Specialization. Because we can do the analysis that, okay, this function here is called with only those types, because we just have the whole program, right? And this is also, I'm not sure if it's done. I know that GCC and MSVC is doing those kinds of optimization. And there is also a very nice thing. So suppose I have functions like this. This actually happens many times, like even in LLVM. We have a function that returns like, is it type of this? Or give me like ID of this dynamic type. So what we can do here, and what is done, is we could extend the vtable and put some extra information like integers or bit masks. And then instead of having a call, we could just change it to load the bit masks and do some stuff with this, right? And this is very nice, especially for CFI, the control flow integrity, because in the CFI mode, before calling every virtual function, we'll have check if this is a valid call, if nobody overran a v-pointer and other stuff. And by doing this, we actually get rid of the virtual calls because we are just loading things from the vtable. That is, we are just loading integers and stuff like this. So this optimization is implemented in LLVM in the LTO mode. Okay, but there is one thing. There is a FinLTO, right? And like, believe me, FinLTO is the best LTO. So first, it solves many problems that we face with strict vtable pointers because we just have definition of all the functions. Of course, LTO also solves those problems, but like nobody really uses LTO because it's very slow. And FinLTO could really change it because FinLTO is really fast. So because we have a vtable that we could import, we have all the functions that we can import, then Optimizer can figure out that v-pointer is not clobbered. It can figure out the v-pointer value from the constructor that we import, and just vtable from just importing vtable. So it is also, we could do all the fancy tricks that LTO do. It's not done yet. I saw the proposal like a week ago or something by Piotr. So it will do, probably, soon. There is one problem with Finality right now, is that it doesn't import global objects. It only imports functions. This is something that, this is because in Finality, like most of the optimization happen, like the best thing that we get is from inlining virtual functions. Just functions. So right now it doesn't import global objects. It could do it, and fix is very easy, but it's not in a priority. And without it, we won't be able to. We won't import objects like vtables. Okay, so I want to thank all the people who work on the devirtualization. I'm not sure if this is the old people. This is at least all the people that I know of from the commits or from the things that people that I worked with. And with this, I'm happy to answer all your questions. Thank you.
Oh, sorry. Hi, John Criswell, University of Rochester. So have you done experiments, say, using profile-guided optimization to determine, or at least estimate, what the maximum performance benefit would be from doing all of this devirtualization work?
I didn't do it mostly because I don't have good benchmarks. Like I started doing some benchmarks with devirtualization on the last internship at Google when I was working on the FinLTO. And like when I went home, I was pretty disappointed to find out that you have to pay for a spec. So I couldn't finish my experiments. I'm not sure how the profile helps here, and I'm not sure how GCC also it's compared to GCC. So I'm not really sure what's the numbers. From the blog post of Jan Kubiczka, who implemented the devirtualization in DCC, there was some significant improvements in some aspects. But I don't really know the numbers.
Okay, so basically what I was thinking, I should probably clarify what I meant by PGO, because it's not quite the right term. Basically, you could profile a program, find all the call sites where it's always calling just one function, transform it to just to a direct call, and then measure the performance, right? And then you figure out what your maximum performance gain could be.
Mm-hmm. Yeah. Unfortunately, we cannot do this. I mean, like we could change it to direct call, but we still have to check if we are calling the right function, because profile could lie to us, right?
So it's not an optimization. It's just an experiment to see.
Yeah.
If you go through all the hoops, what's the best you could get?
So I remember that there was some improvements, like about 4% with indirect call promotion. So yeah, I would guess that it was something like this. I don't really sure like about the number, but this is something that like comes to mind.
Sorry, what?
There's feedback there. You virtualize the call, and then inline you can you potentially turn one virtual call site into multiple virtual call sites, each of which is then potentially further devirtualizable. It might have only a single. Each of those duplicated call sites may then only have a single destination. And so there is some amount of feedback. So it's not obvious that there's a simple answer just from doing that kind of simple.
Okay. Thanks.
Kyle Butt from Google. I just had a question about your assert example in the edge case. And isn't that undefined behavior? Because you're comparing A after you have after its lifetime?
So actually it's not. And this is because this is just a pointer, right? So we can get the value of the v pointer. Like we can just cast it to the integer, and everything is okay. We cannot just dereference the pointer. So yeah, I know that this is like, I was talking with Richard, and there was some thoughts about disallowing it in a C++ 17. Unfortunately, it didn't happen, so we have to handle this. So like, and I also like think that this is the same thing, like, because pointer is just an integer, right? It just points, like, we just interpret it in some way. But comparing pointers should be allowed, even if they are dead.
I've got a question. Have you collected any data on speculative devirtualization when it comes to the code size changes when applying it?
So, I mean, the speculative devirtualization is, there is not even any prototype right now, so I don't have any data.
Okay.
But I think you could find data in this in the blog post of the Jan Kubiczka. There is one big blog post that in many examples like Firefox and other big applications, he shows like what's the differences and how many calls got devirtualized and stuff like this.
Thanks.
Right. So thank you very much.